Okay, hello everyone. Thanks to the organizers for inviting me to a lecture here. It's great to be back in the beautiful town of Firenze and of course at the GGI. There's a lot of things that you could lecture on the topic of advanced general relativity, which I was asked to teach about. And I have decided on a selection of topics that had some recent developments, which range from the deep infrared to the deep ultraviolet. So here we're going to be talking about long distance, low energy physics. And here we'll be talking about short distance, high energy physics. Now on this topic, of course, in the context of gravity, there's of course an obvious question, which is what is the quantum theory of gravity? That's of course a hard question. We're not gonna answer this question in full in this course, obviously. But we're gonna think about a quantum theory of gravity and explore some questions about the quantum nature of gravity in this context, notably on the topic of black holes. So black holes have been a very fruitful playground for questions about quantum gravity. And in particular, we're gonna think about the question, what are the microstates of black holes? Now, when I talk about gravity, I will mainly think about general relativity. And in order to answer questions about the deep ultraviolet, as you know, we need a new theory. So this part of the talk will be about theory beyond general relativity. So that will be the second part of the lectures. The first part will be about long distance, low energy physics. And now you might think, well, at low energy, the theory of gravity, Einstein gravity is general relativity. What's there to learn? So is that not what you cover in your general relativity master courses? Actually, there are questions about the long distance, low energy physics in gravity that we don't know the full answer yet. And even one of the most basic questions we haven't fully understood. And that question is, what are all the symmetries of nature? Now, if there are symmetries that we don't know yet, there may be observables related to that we haven't either found theoretically or observed experimentally. And we're going to talk about that. Now, and this will be about, so this part will be about new insights into known theories, in particular general relativity. Now, these two questions, these two topics, I'm thinking about the infrared and the ultraviolet, are naturally related in the context of what is known as holography in quantum gravity. From the infrared side, the input of symmetries is sort of the first thing that you have to understand if you want to talk about holography, and I will define that in a moment. And then once you have a holographic theory or holographic prescription for quantum gravity, it can then serve as a definition of what we actually mean by quantum gravity via other means. So how does this work? So holography is the statement that there's some theory of quantum gravity on some manifold, M. If this theory has an underlying holographic principle, that means that there is a boundary of this space-time where a theory lives. usually a theory that doesn't have gravity. So it would be like an ordinary quantum field theory that lives on the boundary of this manifold. And we have tools for understanding quantum field theories in the absence of gravity. And if quantum gravity on this manifold is holographic, it means that this quantum field theory on the boundary, in principle, knows everything about what's going on in the quantum gravitational theory in the bulk. We have a precise realization of this holographic principle. In specific contexts where this manifold is a very special one. And that is when we consider quantum gravity on an anti-de Sitter space-time. Let me say in d+2 space-time dimensions, so this is M, which has been shown to have a precise realization or equivalent description as a certain quantum field theory on its boundary. And this quantum field theory typically has a lot of symmetry, so that it becomes a conformal field theory. And the boundary is given by flat space in one spatial dimensions less. So this will be the boundary of this manifold. And by understanding the theory on this boundary, we get a non-perturbative definition of what quantum gravity in the bulk means. So this is sort of the setting where this holographic principle is best understood. There's only one issue with it. So anti-de Sitter spacetimes are spacetimes with negative curvature or negative cosmological constant. And the issue is that our universe has, of course, a positive cosmological constant, albeit a very tiny one. And so we can't directly use the insights that we have learned, and there's many over the past more than quarter century that we have learned about the holographic principle applied to anti-de Sitter spacetimes. We can't directly use this in order to learn about our universe. Now, let's discuss a bit what kind of asymptotic structure we can have, by which I mean a spacetime that contains maybe interesting stuff inside, maybe black holes, planets, whatever, but then as you go far away, they look like anti-de Sitter or some other kinds of spacetimes, for which we can then try to understand if there's a holographic principle. And to discuss this, I'm gonna draw some diagrams, which are called Carter-Penrose diagrams, which we'll discuss in more detail for the specific setting that I will focus on in the course of these lectures. And I'm sure many of you, if not all of you, have seen them already in your undergraduate courses. So for anti-de Sitter, we usually draw this cylinder where so time goes up and space goes sideways. And we're thinking about quantum gravity as being described by the theory inside of the cylinder. And the holographic dual boundary theory lives, well, on the boundary of the cylinder. There are two special features about anti-de Sitter space that have allowed us to understand a lot about quantum gravity in such spacetimes via the dual holographic boundary theory, and even allowed us to set up this dictionary of these two prescriptions. The first is that anti-de Sitter space acts like a box. So whatever is inside stays inside. That's the first thing. So it's like quantum gravity in a box. The second thing is, so this is, you can see the boundary goes along time, so it's a time-like boundary. And this means that we have the usual notion of time. I don't know if this is visible, so this means we have the usual notion of time. And so now you have a quantum field theory on this boundary with a usual notion of time, and the time direction is shared by the theory in the bulk and the theory in the boundary. And this allows us to use ordinary physics that we know from our undergraduate quantum field theory course on GR to understand something about quantum gravity in ADS. Now let me draw the diagram for Minkowski space, or flat space, and we're going to talk about this in much more detail. But let me start drawing it now. So this is what the Penrose diagram of flat space looks like. You see that it's much more complicated than the one found at the Sitter space. In particular, it has these three special points here, and then it has these tilted lines, which, since time goes up and space goes sideways, those are null lines. The two special features that allowed us to make progress and get mileage out of holography and the de Sitter space don't hold here. Flat space is not like a box. That's the first thing. And the second thing, the boundary is not time-like, it's null. And so the time direction is not shared between boundary and bulk. And there is no standard notion of time here. Now this is for flat space when lambda equals to 0. Strictly speaking, our universe has a tiny positive cosmological constant. And the Penrose diagram would be given by this, where this boundary here is now space-like. And the same feature about there not being a standard notion of time, or even no time in some sense, is true for the Sitter space. And it's also not a box. So these two special features here don't hold in the situations which we would like to understand in order to say something non-trivial about our universe in terms of quantum aspects of gravity. And so trying to find a holographic principle for flat space or de Sitter is much more complicated. So you're going to have lectures that relate to de Sitter and cosmology by Guy. For my lectures, I will focus as spacetimes that are flat, far away, for both the first and the second part of the course, so both for the IR and for the UV part. And the reason for that is, obviously, of course, we would like to understand everything and, in our universe, but trying to write down a holographic principle or understand quantum aspects of gravity in de Sitter space is very hard. But the fact that our universe has just a tiny cosmological constant, and the fact that you don't notice that our universe is expanding if you stay at scales that are small enough, that means that it's a good approximation to many processes in our universe to work. So good approximation in the sense that you are far away from sources, but you are below the cosmological scale where you feel the expansion of the universe. And so for that purpose, setting the cosmological constant to 0 is a good approximation. Okay? So much about holography as a motivation, which addresses both, which needs input from the infrared. We need to know what the symmetries are, and it can output you some information about the UV, about the quantum nature of gravity. I mentioned before that I will talk about black holes. Oops. So what about black holes? And in the context of quantum gravity, we have learned a lot about black holes. In the setting of string theory, when this is our quantum theory of gravity. But mostly what we have learned about black holes from string theory applies to special kinds of black holes. So black holes that are supersymmetric, or BPS. And when that is the case, or a bit more relaxed when the black hole is extremo, then we can use holography in the form of the n de Sitter conformal field theory correspondence to learn something about black holes. Now, again, unfortunately, if I put here, what about black holes in our universe, then there's not so much that we know about them as quantum aspects of them are concerned. And so in the second part of these lectures, I'm going to try to push towards understanding some microscopic aspects of black holes as they are in our universe, meaning, again, that I'm going to set the cosmological constant to 0 and try to understand them in the context of a quantum theory of gravity that we know, which is string theory, but not restricting at all to supersymmetric black holes. So the second part of the course will be about completely non-supersymmetric, non-extremal, neutral, rotating or static or rotating black holes, and we're going to try to understand something microscopically about them. Okay, so this is the motivation. The plan of the course is as follows. In the first part, which means roughly the first three or four lectures, we're going to talk about gravity in the infrared. We'll start out with some basics about flat space and what I mean by asymptotically flat space. I will then discuss the symmetries and potentially related observables. We're then going to discuss scattering in the context of with gravitons, in the context of gravity, at low energies, which is referred to as soft physics. We're going to then combine these two topics and talk about something that you might have heard of as the infrared triangle. So this will be some relation about infrared aspects of gravity, which a priori look very different and indeed have coexisted for many decades without being realized that they're actually the same corner of a triangle. And then we're gonna sort of use all this to set up the question of what could potentially a holographic principle for flat space look like. We're then gonna do some intermezzo where we relate some infrared aspects of physics to the UV. This will be one lecture or half lecture. And then in the second part, which will be another 3 lectures, we're gonna talk about gravity in the UV, where I'll first introduce the 2 main players in this context, which are black holes and strings, fundamental strings of string theory. And we're gonna discuss then how we can think of black holes in terms of strings and what this can teach us about some more micro or statistical physics about black holes for objects that are neither supersymmetric nor extremal. And here's a list of references, which I think I've also provided the organizers with, so you don't have to write all of them down. There's some lecture notes, review articles for the first part. There's tons of papers that I could refer to if you have more detailed questions, and we'll mention some as we go along. And then for the second part, there are old papers for when this topic was first, sort of the idea has first been born, and then some more recent works on that topic. Okay. I encourage you to ask questions at any point. If you have one on the motivation, now would be a good point to do so. Don't be shy. The motivation should be crystal clear. Okay, I'm gonna take this as it is. And then we're gonna start with the first part. Okay, so we're gonna start very basic. And for this, let me first gauge where you come from. So I assume you're all PhD students who've taken GR. You've probably all seen the conformal compactification of Minkowski space. Raise your hand if you have. Okay, and keep your hand up if you feel comfortable enough with it to come here to the blackboard and teach it to the rest of you. Okay, good. So we're going to do that now, just to remind you and to have it fresh in your memory, because this will be sort of the starting point for everything that will follow. Okay, so let's start with the metric of flat space. Okay? All good? So I'm using TR theta phi coordinates here. We're going to use other coordinates as we go along, which I will denote by XA, where A are the two angle directions. So this would be, for this metric, it would be theta phi. We will use other coordinates on the sphere later on. And then I'm also introduce gamma AB, which will be the unit metric on the two sphere, which in these coordinates, obviously just given by that. We're going to change coordinates now, because if you want to discuss the physics that happens near these boundaries, so on these 45-degree lines, it's not very useful to work in these TR coordinates. If you want to discuss in particular radiation, which is what we're going to spend a lot of time with, so we're going to use a different coordinate, which is retarded time, T minus R. Where the line element looks as follows: minus du square minus 2 du dr plus r square gamma AB dxa dxb. So this is if we want to talk about the future null line up there. If we want to talk about the past, then it's more suitable to use advanced coordinates, v equals t plus r. And the line element is then given by minus dv square plus dv dr plus r square gamma AB dxa dxb. Now we're interested in discussing stuff that goes out to the null boundary. So that's null particles, radiation. And so it will be useful to look at surfaces of constant retarded time. So here was constant surfaces, which means T equals R. And what's that? Well, that's the light cone. So let's say I emit a message here at, let's say at T equals R equals 0, and this point here, so this will be the U direction. And in this context, this would be U equals 0. So the retarded time, so if somebody emits a signal, then the retarded time tells you, the value of the retarded time tells you at which time the signal was sent. And so this will be useful working with retarded coordinates or advanced coordinates, will be useful for discussing, as I said, radiation. In particular, we will be focused on gravity, so gravitational radiation, gravity waves. Okay, so now let's get to the conformal compactification. So we want to talk about the region near these boundaries, because this is where we want to set up a putative holographic principle. But unfortunately, this boundary is infinitely far away. So what the conformal compactification allows us is to bring this infinity back into some finite diagrams and then be able to discuss various things in a particularly convenient form. So So this is for discussing the place where radiation goes. To Penrose, or Carter Penrose. So you take the entire infinite space-time and transform it into a diagram of finite size with a boundary at infinity. So we have the TR coordinates that we started out with. So let's look at the range. So T goes from minus infinity to plus infinity. R goes from 0 to infinity. We want to transform them. We just did part of that, so we went to retarded coordinates. For the conformal compactification, we want to talk about both the future and the past boundary at the same time. So we go to double null coordinates. So we go to u equals t minus r and to v equals t plus r. That didn't help us with the range yet because u and v still go from minus infinity to plus infinity. But u is constrained by v. In the next step, we're going to make the range finite. So that is usefully done by introducing a trigonometric function, the tangent. So we denote little u by the tangent of capital U and v by the tangent of capital V. So that takes us to a range where this capital U and V are now between minus pi over 2 and plus pi over 2. So we've made the range finite, and capital U is still smaller or equal than capital V. And now if we want, we can introduce back some time and radial coordinate by taking capital T to be capital V plus U and introducing capital R as capital V minus capital U. And then this T coordinate goes from minus pi to plus pi, and R goes from 0 to plus pi. So the range is also finite. And this condition that bounds U by V introduces the constraints that the absolute value of T plus R has to be smaller than pi. Maybe I can still write this here. So once you've done that, we can write our line element as some prefactor times minus, in these last coordinates, minus the t square plus the r square plus sine square r the omega square. Where this here is infinite if you look at t plus or minus r equals pi. So that's the conformal factor. And then this piece of the metric here is regular and has the same causality structure. So as the original line element, which is why it's useful when discussing causal properties to go to the conformal compactification. Okay. So now let's draw this Penrose diagram. So this is T, this is R. Here we have pi, minus pi, plus pi. And now let's draw some special points. So let's first look at spatial infinity. So what's spatial infinity? How do I get there? So this is this point here, denoted by I0. And you get there, so spatial infinity. You get there by taking R to infinity at t fixed. So for example, wow, this is how you can go here, for example. And so what this physically means is that start and end point of space like geodesics. Okay? What about massive matter? Where does it come from? Where does it go to in this diagram? What do I draw? Where should I draw the time-like infinity in the future and past in this diagram? Didn't all of you say, or most of you say, that you have seen the conformal compactification of Minkowski? Where is time-like infinity? And yeah, so this is in this diagram, it says minus pi and plus pi. So this is denoted by I minus and I plus. So I minus would be past time-like infinity. So how do I go there? Well, I'm not going sideways, I'm going up or down. So this means for the past, I go to t to minus infinity at r fixed. And then for future time-like infinity, I go to t plus infinity at r fixed. So massive particles start out here and then go here. Or in this diagram, I could also have them come back to the center and go out there. So let me also say that this point here is, as I've written, at t equals minus pi and at r equals 0, which is this line. And then this here is at t equals plus pi, r equals 0. And I lost my yellow color. This one here, the spatial infinity, is at t equals 0 and r equals pi. So those three are the special points in this diagram. And then we have massless matter, for which these null boundaries here is what matters. So this is denoted as square minus, this is denoted as square plus, and forgive my artistic skills, this should be the same as the line that I've drawn before. This is at t minus r equals pi, and this is at t plus r equals pi, which is the saturation of this condition there. And what's that? So this is future null infinity and past null infinity. How do I get there? Any thoughts? Hint, space goes this way. So let's go towards I equals infinity, right? But now I have to keep something fixed. What do I keep fixed? T fixed gave me that. How do I go there? Yeah, so at u equals t minus r fixed. So u is that direction, you fix it, you go here, right? Different values of u. And here you take v equals t plus r fixed. So this is v. All right. Then what I'm missing in this diagram? Yes? If you take what, 0? Yes? No, sorry. This is not here. This is all of this. So it's t equals r. Oh, sorry, here? Oh, yeah, sorry. Indeed. Thank you. Great. All right, so what am I missing in this diagram? In how many dimensions do we live? Or think we live? 10, okay, 10 is allowed. Other answers? 4. Okay, and this is not 4-dimensional. So we're missing the sphere. Where is the sphere? At every point, yeah, good. Okay, so, except where? Yes, where it's 0 size. Good. So now let's talk a bit about the sphere, which is where much of our discussion will take place, actually. So if I want to highlight that there's a sphere at every point, it may be more useful to, instead of drawing this triangle here, to like double it and draw this diamond, where this is still past and future time like infinity. This is spatial infinity, but I can also draw it here. These are identified. And these are now my null boundaries. Square minus and square plus. And I'm drawing it in this doubled form because I want to highlight that there's a sphere. And now I have sort of twice as many points. So I have a pair of points now that denotes a sphere. So there's a point here, there's another point here. And if you think of this in a sort of 3-dimensional representation, I'm drawing this circle here, which denotes that at the boundary, there are 2 points that denote the sphere, as well as in the diagram. And now I can draw space like GD6 like that, time like GD6 like this funny one, like that. And I didn't draw here a massless matter, so massless matter would come from the past and go to the future. And this would happen like so. So in this diagram, each left, right pair of points at the same value of t and r are points on the sphere that are antipodally related. So what I mean by that is, like, if this point denotes the south pole of the sphere, this could be the north pole of the sphere. So that's that. And now another useful way to draw flat space is to note that Minkowski in 4 dimensions is conformal to a patch of R times a sphere. How do I see that? So if I just take this regular piece here, let me call it ds bar squared. So let me write it again, minus dt squared plus dr squared plus sine square r the omega square. Then this piece here is the local metric on a 3-sphere. And this is what's called the Einstein static universe, which I will now attempt to draw. So time goes this way. Now space will go that way. I'm going to draw spatial infinity for due to my poor artistic skills on this side here, but it could be anywhere there. And then we'll have this, and past time like infinity would be this point here. Future time like infinity would be there. This is the diamonds that I've drawn before. And this here is scry plus, and this is scry minus. And one reason why I'm drawing this is that we'll get back to this fact about points on the sphere antipolarly related later on when we talk about scattering. So if we want to have generators on scry, on null infinity, that smoothly go from the past to the future, so that would mean they come in here and then go out there. So let me draw this up a little bit. So this would be I0. And then if I go along the boundaries, so along here and here, this would be going from a bit on the past boundary here to a bit on the future boundary. So this goes like here and comes out on the other side, right? And if I draw again the sphere, which I denoted by the south pole as a circle and the north pole as this box here. So there's the south pole on the sphere on this side, the north pole on the sphere on the other side. So if I want to have smooth generators along scry, along null infinity, then I should start on one side of the sphere and come out on the other side, on the other side of the sphere. So there will be an antipodal relation as we go from the future to the past. And this will show up later on. So right now it might seem a bit obscure, but this is to have smooth generators on the null boundary as we go up in the future. And this antipodal business will become important later on, and I will go into more detail. Okay? So now let's discuss a few features of the conformal compactification, why this is useful for some questions and not so useful for others. Well, one plus feature is, of course, that we see on one glance what the causal structures of the spacetime, right? You see nothing can, you have 45-degree lines for null particles. Nothing can go faster than them, so there is no more than 45 degrees. You can see what's in the past and what's in the future. So it's a plus if you want to discuss the causal structure. Let me draw this again here. So for past time like infinity, past time like infinity, the whole, what's in the diagram is the whole causal future. So the causal future of this point is everything. Similarly, for future time like infinity, the causal past is everything. For I0, the causal past is scry minus, and the causal future is scry plus. And then if you look at the point in your space-time, the causal past is this, the causal future is that. So that's very nice. A not so nice feature of the conformal compactification is that while it's nice to talk about radiation, it's not so nice to talk about these special points here. Physics of I plus minus and I0 are obscured. And why are they obscured? Well, you told me that, okay, there's a sphere at every point except for the origin, but what about these points? So in the conformal compactification, the sphere goes to 0 at not just r equals 0, but also r equals pi. And so I plus minus and I0 are points. And if you want to discuss, for example, where massive particles come from and go to, that's not such a good way, because it's singular, things will be multi-valued. It's not great. But there's a way out of that, of course, which is to use other coordinates than the ones that we have used to discuss null boundaries. So if I'm drawing this again, and now I make use of my nice diamond over there, again, past and future, and spatial. And now let me draw the light cone of the origin. So in order to discuss the past and the future, as well as spatial infinity, it is convenient to introduce different coordinates than the TR or UR or VR coordinates that we have. And so we want to sort of blow up these points in the conformal convectification. And this is done nicely by choosing slices that approach these boundaries in this way. So you can slice Minkowski space, the past and the future light cone, by these red slices. And the outside light cone, you can slice by the yellow ones. What are those? So let's do I plus minus first. So here we have slices that obey minus t squared plus r squared equals minus tau squared. So these are constant tau slices. And how are these TR coordinates related to this new tau and another coordinate? This is given by choosing the original time coordinate to be tau times cosh rho, and r to be tau times sinh rho. And what this does is it takes the line element to have the following form. Okay. Let's see what I0 does. So at I0, we use slices that satisfy minus t squared plus r squared is, and I'm now using t tilde and rho tilde coordinates. So this is rho tilde squared. And the coordinates t and r are related as follows. There's rho tilde sinh tau tilde, and there is rho tilde cosh tau tilde. And the line element is now d rho tilde squared plus rho tilde squared minus d tau tilde squared plus cosh squared tau tilde d omega 2 squared. And now I'm going to tell you that you have seen that before. Let's start with this one. What is this line element describing? Hyperbolic, yes. So this is hyperbolic 3 space or Euclidean antidesider 3. Bingo. So what this says is that there's a useful way to slice the past and the future light cone of Minkowski space by Euclidean ADS3 or hyperbolic 3 spaces or slices. What about this one here? What is that? De Sitter, yeah. So this is de Sitter 3. So the outside light cone of Minkowski space is conveniently sliced by de Sitter 3. And this is the way to go to blow up the point I0. Okay, let's keep this up. Let me say one more thing, and then we're going to take a little break. Or maybe two more things. So I said that using these slices, we can talk about these blown up points, I plus minus and I0. So how is this done? So the resolution of the singular structure near I plus minus and I0 is as follows. In order to go to I plus minus, I'm going to use these slices now. I'm going to change and going to go to tau and rho coordinates. And since I said, so this is Euclidean ADS3, and then there's this coordinate tau, which labels the slices. So all I have to do is work in these tau rho coordinates and then take tau to infinity. This is how I go up to future time-like boundary. And if I go to tau to minus infinity, I'm going to go to the fast time-like boundary. I0, how do I go there? Well, now it's sort of flipped, the tau and rho tilde, tau tilde. So in order to, so this is labeled by rho tilde. So I go to, rho tilde goes to plus infinity. And this intersects scribe plus minus as tau tilde is taken to plus or minus infinity. So you go out there and you intersect with the future at tau tilde plus infinity and with the past at tau tilde minus infinity. Okay, so that's great. Now we have coordinates in which we conveniently discuss the null boundary as well as these points that are blown up. So another plus about the conformal compactification is that the structure near the null boundaries is very well describable. And in particular, if you want to talk about gravitational waves. However, there's something peculiar about null boundaries, which is one of the whole reasons why we haven't gotten a full-fledged holographic principle for flat space yet, or at least it's one of the reasons. And the reason is that if we look at the induced metric on the null boundary, so again, we work with our regular metric where we pull out the conformal factor. Now we go to scribe, let's say we go to scribe plus, which is given by, in these capital T and R coordinates, it's pi minus R. I still have the metric over there, so let's plug that in. So there's minus dr square plus, so T is R and pi, so that gives me the minus dr square, plus dr square, so this cancels, plus sine square R, the omega square. And so this is 0 times dr square. And so the metric is degenerate. So the induced metric on the null boundary is degenerate. So this is for square plus, but the same holds for square minus. Let me maybe draw this. So let me draw this cylinder where this is the u direction. And here I'm drawing like r times a sphere. So this is my cylinder here. And so sort of this would be the null boundary. And so this kind of sucks. The metric is degenerate, so this means that all sorts of things are either 0 or infinity. And in particular, what this tells us is that, so the S square at scribe plus or scribe minus is just given by the sphere. And I can use rescaling to get rid of this prefactor. So this is just given by the sphere metric. And I also have a normal vector, which is given by d by du. So this is the normal, which is also the tangent, because it's a null slice, a null surface, tangent. And this here has a name. And the name is that this is called a Carolian structure. So this degenerate metric on a null hypersurface with this normal, it's called a Carolian structure. And this has given rise to proposals for holography in flat space that are called Carolian holography. We'll talk a little bit more about that. And so really the last thing before we take a break is to talk once again about the sphere, just defining it. So if you go out to the null boundary, or the conformal boundary, there is a sphere that's located at r equals infinity, which is called the celestial sphere. So located at r equals infinity and u fixed, so that's for the future boundary, the sphere on the future boundary, or at v fixed if you go to the past one. And it denotes all the directions towards which an observer observer at r equals 0 and t equal u can look. And since I mentioned Carolian holography yet, I mean, yes, already. I haven't introduced it yet, but I mentioned it. Let me also mention what is called celestial holography. So there, the idea is that when we have quantum gravity inside of our space-time that looks flat far away, then the sphere, the celestial sphere at the boundary, has a theory living on it that potentially can tell you about quantum gravity in the bulk. So this is something that we will get to towards the end of the first part, which is something that goes under the name of celestial holography. All right, so I suggest we're going to take a little break, unless you feel like you don't need one, but I think we should take one, okay? So how much, 5, 10 minutes, something in between? 10? Okay, let's do 10 minutes, and let's meet back at 10 past 12. Can look. An observer, towards which an observer at r equals 0 and t equals 0 can look. Towards which? Yeah.
What is this picture?
Oh, wow, you have fantastic notes.
I'm just trying to.
Wow.
Okay, so,
Yeah.
okay, so this line is.
Oh, this is you. This is you.
Oh, it's
This
okay.
is the U direction. Sorry. Yeah, you should call me out if I'm writing illegibly.
Okay, so is this
Time. Should be a T, not a plus, of course. This is RT, R sub T.
Oh, okay.
Like that's the.
So
yeah.
R sub T times this.
Yeah, yeah. Mhm.
So this is saying that on the null boundary,
So the.
the metric is like.
So the metric, so if you really go to the boundary, the metric is just the sphere metric.
Yeah.
So that's this S2 here.
Okay.
And then null infinity itself also has time. So the so this is this direction and the circle denotes the sphere. So instead of just drawing a line and saying there's a point at every point along U, I'm drawing a circle to denote that there is a sphere. You could have forgotten about the cylinder. I'm just saying that. So the structure is like a cylinder because you have.
Yeah.
So this is time.
I don't understand.
This
so,
is the
so,
null.
so you're saying any
No,
line.
no. So, okay, forget about this here. So this is inside your space-time. Now we want to go. So here, these were in order to go to that point and to that point or that point.
Okay.
So these were just inside the space-time slices that when you take the slice, so there's like tau 0, 1, 2, 3, blah, blah, blah. If you take tau to infinity, you can approach I plus.
Yes.
And so that means that I plus, which in this compactification in this U and R coordinates is singular. So U and R are good coordinates for this boundary, but not for this point.
Oh, yeah.
So I said, okay, instead of working with U and R, work with tau and rho.
Yes.
Now you tau, rho, and the sphere coordinates denote everything inside these light cones.
Yeah, yeah.
And if you take tau to infinity, you reach that point.
Yes.
Then the stuff that I said here was, okay, now let's go, that was one point about resolving the singular points. Then I said, okay, let's get back to our null boundaries. So these here,
Yeah.
what do they look like? Well, there's the retarded time that parameterizes this direction.
Okay.
There's the,
Okay.
and then there's a point, every point here denotes a sphere. But I can't, so I can either draw points, these are spheres, or I can say, okay, a circle is a sphere, this is my sphere. And then I have like this cylinder structure, because I have like, there is something in R that's denoting this direction, and then, yeah.
I understand.
Yeah.
Thank you.
Okay. Yes?
Nice
Hi.
to meet you again.
Yes, indeed.
So,
Where have you met before? Trieste? No.
Brescia.
Where?
Sorry, what did you ask?
I was asking where did we meet before?
I'm in Amsterdam. I'm a master's student in
Good.
Amsterdam.
Okay. You're familiar, but yeah. Okay. Good. Very good.
Okay, so maybe can you briefly repeat the story here?
Yeah, that's a very subtle one. So if you didn't get it at first, I will come back to this. But the point was just, and maybe I should have drawn this differently, but my artistic skills are a bit poor. So if this is I0, then I have future time like, future now infinity here, and future past infinity there. And then since I've drawn like this, I'm drawing this around it, right? So blah, 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 blah. And yeah. So this would be that thing here. Then I was saying if you want a generator to be smooth across the null boundary, which means I go, so there's I minus somewhere here and I plus somewhere there. So here, if I start out here and I go up here, then I come out the other way. If I want this generator to be smooth, which, here it seems like this is something that we want, then, and this side of the Penrose diagram denotes the north pole of the sphere, this denotes the south pole of the sphere.
What are these 2 poles?
These points are just, the south pole, north pole of the sphere. So there's a sphere, and S2.
So it's a small
S2.
patch on the diagram?
So I can, so if I draw this, I can only, a sphere is a point.
Yeah.
If I draw this, a sphere is a pair of points.
Okay.
That pair of points is I denoted by this dot and by this box.
Okay.
And you can call this south pole and this north pole of this two sphere. So if I want these generators to be smooth, when I do this, but this denotes the south pole, this denotes the north pole, then I need to, as I cross I0, I need to antipodally relate these generators. So if I choose coordinates to describe my path boundary, so there will be VR and then angles, XA. Here I will use U, so here I will use UR and the angles. But if I choose the angles such that these points are south poles and these points over here are north poles, then I have already input in my thing that there's an antipodal matching that goes on when I take the generator all the way up from the past to the future.
So there is a relation.
Yeah, so I can set up the metric on these future and past pieces such that there's an antipolar relation. So what this means, well, in terms of theta and phis, you antipodally relate them here and here. And we'll get back to this in a little while tomorrow. Yeah. Yes.
Hello. I just have a very simple question. When we say holography, we mean quantum gravity. Do we mean string theory or do we mean actual quantum gravity?
So this is, what I'm discussing here is a bottom-up approach. Well, I haven't discussed anything yet, but it will be a bottom-up approach where we start with the physics that we know, and then we try to infer what are the constraints on our putative quantum gravity theory that these known things impose. These known things, we start out with low energy, long distance infrared physics, and we will ask, are there any constraints on the putative theory? We will be agnostic what exactly the quantum gravity theory is. It could be string theory, so I'll make some comments about that. And we don't have that holographic dual yet. I'm just, what I will lecture about is like the first steps towards setting up such a thing. But even the research at this point, we don't know it. So there is a part of this research that is bottom-up, which says, okay, there are these constraints on our theory, but we don't need to know all the microscopic details in order to do this stuff. At the end of the day, we should build more and more constraints such that we really, learn to understand what the dual quantum gravity theory is. That's one thing. And then there's another thing that is a top-down approach. that is also happening in the current research, where people look at toy models. So this would not be Einstein gravity or like your favorite. Yeah, this will not be unitary Einstein gravity because for that we don't know what the quantum gravity theory in this holographic setup is in flat space. But there have been proposals. This goes under the name of Mabuchi gravity or Bern space holography, where there's a string theory starting point, and then you put some defects, some brains in the theory, and then this allows you in 4 dimensions to say something holographic about 4-dimensional asymptotically flat space.
Yes.
Using this input from string theory, there's also some ADS happening because near brains there's ADS spaces. And using this, you can say something about the dual to flat space quantum gravity starting from a high dimensional string embedding kind of setup. So that's something, using string theory as a specific theory of quantum gravity to say something about toy models of 4D gravity.
We do mean, as one of the theory of quantum gravity, we do not believe it to be the actual one or to the.
Well, that depends on who you ask.
Okay.
I will be agnostic about what the quantum gravity theory is. I will try to build constraints on what it should satisfy. Yeah.
And then maybe that's constraints are sufficient.
Yeah, and maybe at the end of the day, it would be amazing if there's just one theory that fits all that checks all the boxes, but we're a long way from there.
Yes.
Yeah. Hi, how are you?
Good.
Yeah. So this is all basic for you. You have seen this before.
Still, we're still having discussions about it because I had a question about when you say quantum gravity on a manifold.
Yeah.
Isn't the point of quantum gravity that you have several a probability distribution across manifolds?
Okay. So
Yes.
I was very rough
Okay.
there. Yeah.
And this Corollian structure. So you're doing another conformal compactification, right?
What do you mean?
At the end. So the first conformal compactification to get the Penrose diagram, but then when we go to some limits.
So I was just going to that boundary.
Yeah.
So I was just looking at what does the metric at the null boundary look like.
Yes.
And then we found that it's not three-dimensional, which it should be if it was ADS, you have a three-dimensional boundary with time. Here we have a three-dimensional boundary. There is U, but the induced metric on that boundary is two-dimensional. And so that is what causes all these issues.
So it's you mean two-dimensional as in two-dimensional degenerate three?
It's a dimensionally degenerate, exactly. The metric is degenerate. The boundary is still three-dimensional. So in order to talk about time evolution on the boundary, there's still time. But the metric is degenerate. So you now have the metric and the normal or tangent. And this is very weird. I'll say more about this later.
Okay.
But yeah.
I guess already at the level of the action.
Yeah, we don't know what the intrinsic action is at these null boundaries that tells us how to do scattering from the boundary point of view. We don't know that. People have made progress in discussing some parts, but the quantization of whatever actions people have come up with, I'll say more about this and how to think of Corollian theories later on. Yeah. Okay, so before the break, I reminded you about some basic facts about flat space. Now we're gonna do something a bit more exciting. which is I put here in front asymptotically. What that means is you want to have a space-time that captures interesting stuff, not just an empty space where nothing is going on, right? That's boring. Even though we saw that there are some aspects that are not quite trivial. So now we're going to do asymptotical flat space, and that means that whatever interesting stuff you have going on inside your space-time, as you go far away, an asymptotical flat space-time is one that as you go far away, it looks flat, to leading order. And what that means to leading order, I'm going to discuss now. So in order to discuss what that means, we're going to use a framework that is very convenient, and again, convenient to discussing the place where radiation goes. And this is the Bondi-Sachs formalism. So we're going to use coordinates u, r, and the angles. And again, we're going to focus now on the future boundary. Same goes for the past boundary, where again, a are the angles theta and phi. And we're going to center our discussion again on light cones. So there's a light source at the origin. And we're going to look where that goes. So we're going to look at outgoing null rays. These are the things that reach the future boundary, future null boundary. So we look at u equals t minus r equals constant surfaces, which by definition are null hypersurfaces. So if I draw again this 45-degree line, which denotes u, then we're going to look at some u equals constant surfaces. So we want to now write down general metrics near the boundary that are geared towards describing null rays. So the first thing to note is that the normal to a null hypersurface where u is constant is null. It's also geodesic, and it is also tangent. As a peculiar feature of null hypersurfaces. And what this tells us is that the upstairs UU component of the metric vanishes. Okay, let me do a little side computation to motivate this. So the normal here, so n is n mu d mu, where d mu is du, so this is just minus d mu u. And the sign here is chosen such that n mu, the normal with upper index, has a +1 here and a +1 there. So this one is, we want it to be future directed. And this +1 here is that r should grow along the light ray. We want to go out to infinity. And the fact that it's null comes from looking at n square. I mean, so it's null, that's the fact, and how GUU behaves can be seen as follows. So n square is just g mu nu, n mu, n u. That has to be 0 because it's a null hypersurface. And then from there, you just see that GUU, because there's only something non-zero when n mu and n u are nu and u. So this has to be 0. So that's that. Then, furthermore, so we have u equals constant. We would like r to grow. And we want the angle coordinates to be constant along the light ray. That gives us another condition on the metric, which now involves the u and the angle components and tells us that they have to be 0. Now I can take these two conditions and pull the indices down using the metric, and then this tells me that the lower GRR component have to vanish, and the lower GRA components have to vanish. So this is by the coordinate choice that we made, so this is a gauge condition on the metric. So we're picking a particular gauge, the Bondi-Sachs gauge, where the lower RR and RA components of the metric have to be 0. There's a third thing that I would like, which is that R is an areal coordinate, which means that this coordinate R is such that the area element grows as R square. So I want to go outward following the light ray and my sphere becoming bigger. So that means that the determinant of my angular components of the metric, that would be GAB, have to start with R squared times stuff. And so that means that the GAB here has to start with something in R squared. And then some metric that doesn't depend. Well, the leading term doesn't depend on R. I can also take this condition now that I've written in that form, and that gives me, so the fact that the determinant of this metric, which I write as R squared times HAB, is of this form, gives me a condition on what this H has to satisfy. So if I take dr of the determinant of HAB, I have to get 0. Okay? So those are 3 conditions, 3 gauge conditions on my metric. So let me write this out now. So we're looking now at some general metric in these coordinates. They have a UU component. They have a UR component and a UA component, and then the angular pieces. They have no RR and RA components by these conditions. And this angular component has to go like R squared HAB, where HAB satisfies this condition. Okay. Let's look at what this fits. So if we were in flat space, we have learned what the metric looks like in this retarded Bondi coordinates. So in flat space, this GUU, what would it be if you remember from before? -1. GUR, -1. GUA, 0. And then this HAB, that was the sphere metric, right? R squared sine squared theta or gamma AB. All right, so this is one example, but there's more, more spacetimes that fit this structure. But let's count first what are the free functions in this form here. So, so there's one here, right? There's one there. Because there are 2 angles, there are 2 here. And then here, in principle, there would be 3 here. But then because of the determinant condition on H, that 3 becomes a 2. So if I add them all up, it tells me that in this form where I have chosen these sort of gauge conditions, I have 6 free functions. And depending on what you choose for those functions, you can cover different spacetimes. Okay. So now let me tell you how to go from flat to asymptotically flat, what I mean. So asymptotic flatness. So this means I approach Minkowski space asymptotically, duh. But how? Well, I approach flat space or Minkowski space as I take R to infinity at U fixed. That's if I want to go towards the future part of the boundary. If I go to the past, then I have to replace all the u's here by v's, have to put in some signs. But the same story goes through, and then I would go to v equals fixed. And so this is an expansion in 1 over r. So let's write this out. So we said here we start with a -1, then there's dot, 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 the u square, plus 2, again -1, plus dot, 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 du dr, plus 2, then we just have dot, 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 du dxa, and r square, we start with gamma ab, and then let me say the first term starts with 1 over r, there's dot, 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 dxa, dxb. And this thing was the HAB. Okay. So now the question is, so if we want to approach Minkowski space asymptotically, so those are the first terms. But then the question is, what is space-time, what are the boundary conditions of this space-time actually, what they are? And this lies in the dot, dot, dots, right? So these dot, dot, dots contain information about what's inside the space-time. And we're going to focus on fall-offs of space-times that were chosen by Bondi, van der Burg, Madsen, and Sachs in the 60s. So that's BMS. Unfortunately, van der Burg always gets dropped, so maybe I should write B square MS to be inclusive here. So they have told us what these dotted dots should be to capture interesting physical processes. So the first one here, which goes with this retarded time square, is something that goes like 1 over r, and they call this coefficient m, or sometimes mb, but that's too much notation. I'll call it just m. Then, and let's think about a space-time that's physically of interest. Like, what is your favorite space-time? Yes, great. Mine too. So Schwarzschild. Then if you look at the time component, it starts with 1 or -1, and the next term is 1 over r, and what sits in front of the 1 over r is what? In nice coordinates, Schwarzschild mass. So the mass of the black hole has something to do with this m here. Now let's go to our next favorite space-time, which is what? No. Asymptotically flat, not this either. Kerr, excellent. So in Kerr, we're going to look at, well, what's the special thing from Schwarzschild to Kerr? We spin a black hole, right? So, and what's the spin? It has to do with some Killing vector that goes in that is with respect to what direction? So yeah, so there's some angle, and so these are the angles, so there's time and the angles. So this will tell us something interesting about these dots. Turns out in these coordinates, we first start with some dots, and then this thing has some interesting piece, which is the 1 over r piece. And that has something that I will denote by NA. And maybe you can guess what this will have to do with. Yeah, so there will be something there. And now for getting, well, okay, well, there's something interesting that we can do with black holes, which is what? Let's say with two black holes. We can smash them at each other, right? Make them merge. What happens when black holes merge? There's radiation, okay. How do we describe radiation here in these spacetimes? Well, that will actually come in here in these dot, dot, dots. So there will be something that's called CAB, which will tell you something about radiation, okay? And then that piece here, let me just tell you what Bondi, van der Burg, Madsen, and Sachs did here is they said this should be of order 1 over r square. And this here should be of order 1 in r. So these pieces here, M, NA, and CAB, they are functions of u and the angles. Oops. And now, since we have picked already some spacetimes, we have put already in some matter or radiation content. So we have to say something because you have just written down a geometry. And what does a geometry need to satisfy if you want to have it be, some physical, caused by some physical matter or radiation? Yes, we need to satisfy Einstein's equation, so this should be consistent with Einstein's equations. Right? So I may choose on the right-hand side here some matter content. And then the way that this matter stress tensor falls off has to be consistent with the fall-offs that I've chosen here. Otherwise, this equation will not be satisfied. So since I have here these three functions, m, na, and cab, if I want to impose Einstein's equations, what this means is that it gives me constraints on the evolution of these functions. And in fact, it gives me only constraints on the evolution of m and na. And we'll talk more about that in a second. So the evolution of m and na, so evolution in time, in retarded time u, is constrained. And what Einstein's equations also do is they determine for us these dot dot dots that I've written out explicitly as, all the dot dot dots that are not the functions that I wrote here. So this dot 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 and that dot 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 in particular, in terms of m and a and cab. Okay, so an aspect of this metric is, well, we have already seen it captures our most favorite spacetimes. So captures black holes, gravitational waves. All right. Can you see if I leave this here, or is the screen blocking some of you? Okay, then you all captured what's written here. Okay, let me leave it like that for a moment. Like this. Okay. So now let me talk a little bit more about M and A and NAB. So M is called the Bondi mass aspect. It is a function of u and the angles, and its evolution in retarded time u is constrained. I will not write that down because it's an ugly looking expression. Because we have the angles here, this is actually an angular density. And if we were to integrate this over the sphere, we get the Bondi mass, which is a function of u. So d square x will denote my angles on the sphere. The induced metric now here is gamma from the gamma AB. And what does this tell us? Well, if I have radiation that goes out, so if there's some flux, then the evolution equation of this Bondi mass aspect will give me what's called flux balance laws, which essentially tell you that mu decreases if there is flux through scry. Oops. So if something leaves, then, well, the mass goes down, right? So that's one thing. Next, we have NA, which is called the angular momentum aspect. It's also a function of u and the angles, and Einstein's equations constrain its evolution, yes? flux balance laws. Flux balance laws. And then it says that the Bondi mass, m of u, decreases if there is flux through scry. So if you have no flux, then it's constant along the boundary. But if you have flux, well, then you had more mass than before because flux has left. Flux has taken away energy. That's why flux balance laws. Yeah. Okay. Then we have the the angular momentum aspect, and again, this is an angular density. So I can go to angular momentum. By integrating over the sphere. And now I have an index here. It's a sphere and index. So I have to contract it with something. Well, it has a sphere index, so it should be a vector field. And can you guess what vector field this has to be such that this makes sense here and has something to do with angular momentum? So we're going to discuss symmetries towards the end of this lecture. And this vector field will have to do with Lorentz transformations. Because if you look at Lorentz transformations or like Lorentz symmetry, there's rotational symmetry in there, and therefore angular momentum, which is the charge of that symmetry. And then this other function, CAB, this is called the shear or the free data. So this is CAB, also a function of u and the angles. It has the property that it is symmetric. CAB equals CBA. And that is clear because, well, the metric is symmetric, right? So this shows up in the metric. And then another property is that it is traceless. So if I use, in order to lower and raise indices on the sphere, I use now the metric on the sphere, gamma AB. So gamma AB, CAB is 0. And what that means, you have these two conditions. And these two conditions boil down the physical degrees of freedom inside CAB to 2. Can you guess where this is going? Yeah. So by imposing symmetric and traceless, we're going to two polarizations. And this then has to do with gravitons or gravity waves. So CAB has something to do with gravitational radiation. To make this a bit more physical, let me introduce what is called Bondi news. This is just the u derivative of this shear, the u CAB. And since we were talking about flux, flux of gravitational radiation is given by the square of NAB. This is very similar to in electromagnetism, where you have essentially FUA. You square that, you get the electromagnetic flux. Here you square NAB to get the gravitational flux. Yes? It will be the vector field that is associated to Lorentz transformation, so to rotations on the sphere. And yeah. Well, I mean, there's like rotations. If you pick the rotation ones, then this will have to do with angular momentum. The flux, the gravity flux, gravitational flux. Yeah. Yes, I mean, yeah, eventually. Indeed. So NAB is the flux. And now I said this is also called free data. Well, why is that? It's because the evolution of CAB is unconstrained. So Einstein's equations don't tell you how du CAB goes, while for the Bondi mass aspect and the angular momentum aspect, there was an equation. And that equation the du of little m and the du of Na had something on the right-hand side. That something involved the matter stress tensor up there, but it can also involve this quantity CAB, or the time evolution of this quantity CAB, so the bond in use, and its squares. Okay, so this is sort of the free data. It's something that's up to you to choose. And then the rest will be constrained by imposing Einstein's equations. All right, so now we're going to come to the second topic, which is symmetries. And this symmetries and observables, and this first part will be focusing on symmetries. Okay, I think we have sort of 5 minutes left, so let me start outlining this, and then we go into more detail tomorrow. So we have now set up the stage. We have defined what we mean by an asymptotically flat space-time. It looks like this. It has three functions in there, which are a priori free, but when we impose Einstein's equations, two of them have their time evolution constraint. One remains free. And now we would like to discuss a bit what the symmetries of such spacetimes are. Let's first discuss isometries. So the isometries of Minkowski space. What are the isometries of Minkowski space? Poincaré. Which are Lorentz transformations and translations. Now, you all know how to write them down in Cartesian coordinates. Let me write them down now in these UR theta phi coordinates. And let me do that at scri plus. So, for example, rotation around the three axes, which is just x1 dx2 minus x2 dx1, in these u, r, theta, and phi coordinates is just given by d phi. A boost along the three direction, which in Cartesian coordinates is x0 dx3 plus x3 dx0, is given by something that looks like minus u cosine theta d by du minus sine theta d by d theta. And then let's do another one. So that's for Lorentz as an example. And then for translations, let's just look at translations along time t, which in the u r theta phi coordinates is just d by du. So these are examples. Actually, those are the nicest examples. If you do the rotations in 1-2 directions, or the boost, or the other translations, it looks much more ugly. So this is the price that we have to pay. The isometries look a bit more complicated in these coordinates. But we soldier on. So what is an isometry now more general? There exists a vector field. So a vector field psi is an isometry if and only if it satisfies special equation. What is that equation? That's the Killing equation. And what does it look like? Well, it says you take the Lie derivative with respect to this vector field psi. I'm looking at flat space here, so eta mu nu would be my flat metric, and you impose that it's 0. Or equivalently, you can write down that the covariant derivative nabla mu psi nu symmetrized vanishes. Okay. Okay, what do we have? So if such an isometry exists, then I can construct a conserved current. Let me call it J. That satisfies dj equals 0, and whose integral over an arbitrary Cauchy slice produces a scalar quantity. And that is the charge. So Q is an integral over some Cauchy slice sigma over this current J A. And this dSA is the surface element times the unit normal NA to sigma. So for example, we just have looked at translations. Conserved quantity is P mu of T mu 0. And then Lorentz transformations give us a conserved quantity J mu nu x mu T mu 0. This is, of course, energy momentum. And this is angular momentum. Yeah, let's do it like that. Yeah, I may have been a bit sloppy with Hodge stars. Okay, so I think I'm out of time now, so let me just say that, okay, so this was about isometries of flat space. We don't have asymptotical flat space, so we can't talk about isometries, but we will talk about the next best thing, which is what we're going to do tomorrow, which is we want to look at something that satisfies the Killing equation, not exactly, but asymptotically. So what this means is that we will, instead of this equal sign, we will say we want this to be satisfied asymptotically, by which I mean that we go to r equals infinity. So as we approach r equals infinity, we want this equation to be satisfied. So there will be a 1 over r expansion that we're doing, like what we did for the metric, and we want to impose that this has to be satisfied for our asymptotically flat metric G mu nu. And then we're going to derive what this vector field has to be. And this will tell us some surprising fact about spacetimes that are flat asymptotically, where the curvature is weak, that may go against our intuition from, I guess, undergraduate or master level physics, where we learn that as gravity is weak, we can do quantum field theory, which means quantum mechanics and special relativity, and we know well what the symmetry group there is. That's what you told me. Okay, so that's it. Do you have any questions? Yes? Why? Well, one is you may start, as we did, write down your most favorite metrics, and then see what structure they fit. So, for example, if you didn't have this 1 over r here, but let's say you imposed 1 over r square, then you wouldn't capture the Kerr metric by this. Yeah. Here? If you impose these fall-offs, okay, let me think. So at one place, you use the equations of motions, which tell you how some components fall off. So for example, once you chose this, this, and this, then it will fix for you this one in terms of the other. So this would be overleading compared to this 1 over r. But it gets fixed by Einstein's equations. This, I think, for this one as well. So I think for this to satisfy the bill with Einstein's equations with some matter that has some fall-offs, these are determined like so. Somehow it kills the 1 over r term. But I do not remember well, so don't take my word for it. You can try to work it out as a homework exercise. Yes. In general, in this Bondi-Sachs frame, or more generally speaking, if you want to discuss general spacetimes with some boundary conditions, in a sense, you could say it's up to you to choose some boundary conditions, and then you have to see if, with those chosen boundary conditions, you capture all the physically interesting spacetimes that you want to capture without getting pathologies. So if you chose some crazy fall-off, and by crazy, you might not know this beforehand, you might just realize it afterwards, you may get infinite energy flux or some negative mass or something that you may not want to have on physical grounds, and then you have to change your answers for your boundary conditions. On the other hand, if you were to tell me what kind of interactions that you want to have in your theory, like interactions between, let's say, gravity and matter, then this sort of imposes on you what the fall-off of, let's say, the metric field or matter fields are. So there's these two ways, either using this sort of Bondi-Sachs framework where you do these 1 over r expansions, and then you have sort of all the interactions in this 1 over r expansions without distinguishing the leading interaction from subleading and so on. Or, and this would be using another gauge, not the one that we have chosen. There's another way to discuss, I mean, there's many ways, and it all is choosing different gauges in some sense. There's another way where you say, okay, I want to write my metric as the flat metric plus perturbations in the coupling, and then you organize it in terms of orders in the coupling. Here what we're doing is we organize it in terms of 1 over r expansion, which is very different from that sort of perturbative in the coupling expansion. And both these approaches are useful. I will switch to the second one later on, but this is sort of maybe the easiest one to introduce the discussion of symmetries. Yeah. Yes. Yes, and you might wonder, can you get some, can you mimic how you go to the asymptotic boundary, how to describe holographic dual to quantum gravity in asymptotic flat space by doing a Pfefferman-Graham-like expansion. And this would then sort of, this is going a bit ahead, but this would then give you what I referred to before as Carolian holography, which is where you look at this codimension 1 boundary in asymptotically flat space and try to make sense of theory living there. So that would be, yeah. There's different gauges that you can choose. I have started with one, the Bondi-Sachs gauge. I just mentioned another one where I do everything in terms of expansion, in terms of coupling, and not 1 over r, which is another way to do it. This one usually works in what's called the Donder or harmonic gauge. We're gonna get to that later on. Then there's other gauges, other ways to fix some metric components and then say what happens to the others. And they're useful for different aspects of, gravity at large distances. Or, yeah. This is not the only way to do this, but it's the one that I've chosen to introduce perhaps as fast as possible where I want to get. Although not very fast because we didn't even get to the asymptotic symmetries yet, but we'll do that tomorrow. More questions? Yes? Excellent. Great observation. So when I write Minkowski space in Cartesian coordinates, then this is just 0, this term. And then I have 1 over r corrections. Now I've gone to these UR XA coordinates, where there's a subleading term that happens to be r to the 0. Yeah. So if I wrote down the flat metric, and then I went to these URXA coordinates, then I wouldn't write this term. And you might have thought, well, then it should be 1 over r in these coordinates. But it's 0 in like Cartesian coordinates. But then when I go to these coordinates, the subleading component is order 1. And it cannot be anything. It's fixed by the other ones. It's fixed in particular by a derivative of this CAB term. And there's nothing I can do about that. That's just Einstein equations. Great. Very astute. More questions? Because otherwise we're done. I think, right? Yeah, there's lunch. Okay, see you tomorrow. Or, yeah.